Okay, are we up and running there? All right. Hi, everyone. Thanks for joining us. I'm Deb Lavoie with Reality Team, and today we have Professor Zeb Page with us. Zeb is an associate professor of geology at Oberlin College, and I had the opportunity to listen into a lecture he was giving to a group of high school seniors. What struck me about this lecture, which was on climate change, was that Zeb was not just lecturing about the facts, he was not just presenting data, but he was really helping these students understand how scientists think about these issues. And he's just the science teacher everyone should have had or hopefully will have. So thank you, Zeb, so much for joining us today.
Well, thank you very much. I'm happy to be here, and thank you for those kind words.
Absolutely. I think that climate change is one of these topics that either tends to be slogany or super technical. And that makes it really hard for us to sort through what might be true and what might not be true. And I thought you'd be a really good person to help us understand why scientists are so certain about climate change, what brought them to that, and where we go from here. So first of all, can you talk a little bit about what it means to be a geologist, the kind of geologist you are, and how that relates to climate change and how it informs climate science?
Sure. Yeah. There's a lot of different names that we call scientists who study the planet and the history of the planet. Geology is the traditional one. People talk about geosciences, people talk about earth sciences. But I often like to think about, the name of the museum that a lot of us used to go to as kids was the Natural History Museum. And they've changed that a lot, but I really like the idea of natural histories, because what we do is we use all sorts of tools. Sometimes they're fancy chemical tools, sometimes it's measuring things in the field, sometimes it's fancy physics tools, but we use them to learn about how our planet works as a really complicated interconnected system. And we use them to talk about the history of our planet and how it's changed over time. So my little piece of that in my research is I work on metamorphic rocks, pretty sparkly rocks with minerals in them. And I use a whole bunch of, I'm a geochemist, so I use a bunch of chemical tools to use them to tell stories about how mountain ranges form and how the plates on the surface of our planet move around. But they're also the exact same tools that a lot of people that we use to understand the history of climate on the planet in detail. So I've worked in labs with people who do that work. I've helped them with some of their work. They've helped me with some of my work. And I teach it. So yeah, it's really all kind of one. It's more of a way of thinking and a way of using data to understand the history of our planet.
So when we're talking about the history of our planet, and in particular the history of our planet's climate, what does geology have to say on that subject? Like, what do you look for? Like, how do you know what happened with the climate over these, periods of time that are hard for us to even understand?
Yeah. Well, the first thing that we have to realize is just how phenomenally old the planet is. It's 4.5 billion years. That's 4 or 5, and that's 9 zeros, and it's a lot. And sometimes it's as simple as looking at a rock and recognizing the environment that it formed in. So sometimes if you're on a dry summer day, you can see a mud puddle that has dried up and has cracks in the mud. Well, sometimes mud puddles like that get buried and enter the rock record. And if you see one 300 million years later, and you see a lot of them, you can say, well, this was kind of a hot, dry place. So, I think a lot of times people, think, well, didn't this part of the planet used to be under the ocean? And that's true for most of the parts of the planet. But I think it can start with just recognizing, just if you learn to look at rocks and read rocks and understand the climates that they record, one of the first things that immediately becomes apparent is that there's been different climates all over the planet, for a long time. There are fossil palm trees in northern Alaska from not that long ago. And so you find a palm tree, that it it used to be warm.
Like not that long ago?
Okay.
You mean really actually long ago?
Sorry, thank you for catching me there. Yeah, like 20 million years. So yeah, that's pretty long, I guess.
So in normal thinking, that's a long time.
That is a long time ago. Thank you for catching me there.
But in geologic time,
it's
so long.
Yeah, no, it's 5 minutes. So
and that's interesting too. So when we talk about what science has learned about the history of climate change, we hear that, oh, well, the climate has always changed. Has the climate always changed?
Yeah, the climate has always changed. And I think it's one of those questions where it's really important to ask, well, you could say that, is it cold outside? Well, it depends on whether you're wearing a down jacket or shorts and a bathing suit, right? I mean, yeah, you get kind of a different answer depending on what you're prepared for. So our planet has a really long history, and sometimes in that history, it has probably been completely covered in ice all the way down to the equator. And other times in that history, there's been no ice at all on the poles, and sea level has been high, and there was an ocean across the middle of the United States. And so all of that has happened. But as we get closer to thinking about the situation we're in now, we have to ask ourselves, what kind of world do we want to live in? Just because it's been that way in the past, I don't want to live in a world that looks like, Hoth and Star Wars.
So
the opposite.
I don't either.
Yeah.
So what do we know about what caused climate change in the past, and like those scale of time across climate change? Because if you're saying, 20 million years ago was just 5 minutes ago, when you talk about history of climate change, are you talking about changes over 5 minutes, meaning 20 million years? Or help us think about what we know about what changed climate in the past and over what time frame it changed.
Sure. Yeah. So climate change is I think we were talking about this earlier about how climate change, it can be really complicated. And so if you look at it in a huge amount of detail, it can be overwhelming. So one of the ways to start thinking about it is that there are sort of three big levers. There are three big things that control the temperature that we experience. And the first of them is how much sunshine we get. And we experience that daily, right? And it's warmer in the day than at night because the sun is pointing at you. And we experience that on a yearly climate change because in the wintertime, you're pointed more away from the sun and you get less sun, so it's colder. Well, there's a whole bunch of other cycles that are much, much slower that are really hard for us to understand as humans, cycles on the order of tens of thousands and hundreds of thousands of years. So sometimes it gets warmer and colder, and these are these natural orbital forcings. So that's one. The other one is kind of how thick
sunlight.
That's the sunlight, how much sunlight we're getting. Number two is how much sunlight we keep, and it's got a term called the albedo, but it's kind of like if it's a hot summer day and you're wearing a white t-shirt, you're going to be more comfortable than if you're wearing a black t-shirt. Though if you have more light colors on the surface, it bounces that sunlight back. So if you have a lot of snow, then it tends to stay colder because it bounces the light back. So that's two. And then three is the one that we're talking about all the time. And that's kind of like how thick a blanket is the Earth wearing. And the blanket is the atmosphere and it's greenhouse gases. So if you have a lot of these greenhouse gases like carbon dioxide, the sunshine comes in and that heat energy is trapped in the atmosphere and it keeps it close and tight. and it helps you warm up more. So you have these three things that play back and forth and affect each other, and you end up getting kind of a complicated set of changes.
And how do we know? So we have the fossil record and the geological record to understand things like how much ice and snow might have been on the Earth. How do we understand how much carbon was in the atmosphere 100 million years ago?
Sure. So so that's kind of where the geochemistry comes in, and the natural history. We have these theories about how the whole thing works. Then we have to go and find. This is where earth science is maybe a little bit like history, a little bit by archaeology. Not in the same way, in the sense that you have to find some material that has a record. So for the longer term, for hundreds of years, we use shells. The shells of creatures living in the ocean. And the way that they incorporate the oxygen and the carbon from the water into their shells is able to give us a record of temperature and some sense of the chemistry of the water that they lived in.
And then what about these big chunks of time, these 20 million years and forward? Do we have to go find palm trees in Alaska? And
well, it is kind of, in a way, it's kind of like history in that the further in archaeology, the further you go back, it's harder, you have less information. So if you go back hundreds of millions of years and billions of years, you have to look for those just really general signs like palm tree fossils or something like that. As you move into sort of the middle range into the millions of years and tens of millions of years, you can use these fossils that we find in the ocean. And when you look at a shorter time range that's still really long for us, say 300,000 years, that record is preserved in ice. So ice cores from various glaciers, but particularly Antarctica, have a record not only of the temperature that comes from the different isotopes that you can analyze, but also has little gas bubbles and has little trapped samples of the atmosphere. For 350,000 years, which is not so long for our planet, but is really a long time for people. So that gives us a really detailed record.
Okay, so the climate has always changed. It has changed over long periods of time, short periods of time in the past?
Yes, both. Earth scientists and geologists used to spend a lot of time arguing, does everything happen really, really slowly, or do things happen really, really quickly? And the answer is yes. Sometimes they happen really, really slowly. But volcanoes are a thing, and meteorite impacts are a thing. So over time, you have these three levers of how much sunshine gets in, how much is bounced off, how much greenhouse gas there is. And then every once, and those changes are relatively gradual. So they're changes where in a human lifetime, you might notice that it's colder when you're an old person than when you were a young person, but you don't understand how much it's shifting. This would have been like the last ice ages. Then very occasionally, something really dramatic happens. Sometimes it's volcanic eruptions, sometimes it's meteorites, sometimes it's human beings who discover fossil fuels. And these seem to can create very sudden changes in the planet.
So the kinds in the past, when there has been sudden changes, or the kind of changes that you measure over, say, 150 years since the Industrial Revolution, what has happened to the Earth in those, when the climate has changed in those sort of either very sudden or generational periods, human generational periods?
Well, bad things. Bad things happen to plants and animals. We often, sometimes people say really dramatic things like, the Earth is going to die. And for an earth scientist, we say like that's not true. It's been here for a really long time. And we have evidence of really, really bad things happening in the past. And the Earth is not killed and life does not disappear. But I think the next question is like, well, is that something that anyone wants to live through or try living through? And the answer is no. So an example, there have been a number of mass extinctions in the history of the planet, and they generally coincide with really rapid changes in the climate. 250 million years ago, there was a huge amount of volcanism, massive amounts of volcanoes in what's now Siberia. And so much lava came out that the gas that came out with the lava really, really changed the composition of the atmosphere. And it made it much warmer, and also, which is what's happening today. And it also put a lot of acid into the oceans. And it resulted in the largest mass extinction in the history of the planet. It's not only 90.
And what does that mean? So, did the nature of continents change? Did some plants and animals shift? Or was that a global phenomenon, or what do you even know?
It was a fundamentally global change in the nature of life on this planet. Most of the living things on the planet died. Now, I'm not saying that that's what's happening right now, but it has happened in the past, and it's happened multiple times. It was a long time ago, so a lot of the details are not very clear, but so much changed that it allowed for brand new sorts of animals to evolve. So the origin of the dinosaurs, and in fact, the origin of mammals, our ancestors took advantage of the huge amount of death at that time to be able to find new ecological niches for themselves. So on one hand, you can tell a story as if it's, the amazing nature of life, that evolution and life sort of remakes itself and can transcend huge tragedy. On the other hand, you could say, well, I would really rather not have to experience a huge tragedy. And I think that's where we are today.
Right. So the Earth will go on. The question is whether we go with it, and whether we go with it in a way that is not torture to us. And as we were talking already, we're already seeing some people affected by climate change already. And what we've seen is about 1.1 degrees Celsius, which is like 2.4 degrees Fahrenheit. And, most of us think in Fahrenheit. Is that right? So when there was these massive extinctions in the past, do you know how much of a temperature increment there was, or is that?
I don't actually. And I think that for example, the example I am giving a really dramatic example, that the Permo-Triassic extinction was the worst thing that we know that happened to life on this planet. Although there's some theories there were possibly an even worse one much earlier in the planet. But so that is an example of probably more than just temperature, but also really atmospheric chemical changes. So it's hard to make a direct comparison. But there are many other extinctions that are not quite so bad, but still that really changed life and make things very difficult for some animals and plants. And those are often tied to really rapid changes in atmospheric chemistry. So bad things happen when the chemistry of the atmosphere changes quickly.
So bad things happen when the chemistry of the atmosphere is changing too quickly. Is the chemistry of our atmosphere changing very quickly right now?
Yes, sadly it is. I think most of us have heard about the increase in carbon dioxide. And I think it's an example of when we're talking about geological time, things happening slowly, things happening quickly. Well, human technology and the developments of human technology, as you were saying, in the last 150 years since the beginning of the Industrial Revolution, is really kind of unprecedented for any animal. I'm saying the human animal on this planet. And the power for all of this technological change, or the vast majority of it, has been from fossil fuels. And that's carbon that was naturally removed from the atmosphere over millions and hundreds of millions of years. And we've dumped it out into the atmosphere at a much, much faster rate, geologically instantaneous rate. So it doesn't really.
When you say removed, you mean that living things have carbon in them, And when we burn those living things, or those formerly living things that are now fossil fuels, those things that hundreds of millions of years ago were dinosaurs are now coal or oil, then we burn those things, that releases the carbon that was in those things into the air. Did I get that right?
Yeah, that's right. I mean, really, it's plants. Plants take the carbon dioxide out of the atmosphere and store it into carbon, which is like, and mixtures of carbon, like sugar. Sugar's got lots of carbon on it.
Sure.
So when you eat a banana, you're putting that sugar in your body, but that banana tree made that sugar from the carbon dioxide in the atmosphere and various other things. Which is why when people think about planting trees, planting trees can help combat adding carbon dioxide in the atmosphere because it takes carbon dioxide out. As long as that tree stays a tree. But if you burn that tree in your fireplace, you're sending it right back out. And burning wood is one thing, but if you're burning gasoline, which comes from ancient marine life, or you're burning coal that comes from ancient plants, that's taking the carbon that was removed from the atmosphere millions of years ago and putting it in the atmosphere now. So we're mixing up the balance. We're tipping the scales in the same way that a huge volcanic eruption might tip the scales by putting gas in the atmosphere very quickly.
So the atmosphere is changing very quickly, and scientists seem really sure that it's because people are burning fossil fuels. That's the cause of that rapid change. Why are they so sure? Why is there so much consensus in the scientific community that we are causing this problem by burning fossil fuels?
Yeah, that's a really great question, and I think it's something that's on a lot of people's minds. One of the things that it's important to realize about scientists is that scientists like to argue a lot. I mean, people like to argue a lot, but scientists love to argue a lot. I've got my thing that I'm working on. Somebody else has got their thing that she's working on. We're a little bit different. We want to have an argument about it and figure out which way it works. And this is an example where it's sort of, there's all this stuff that's like, yeah, all the scientists working on this agree. And it's one of those things where you look at the record and it's just unequivocal. You look at the record for the last, decades that are measured from Mauna Loa, and we see the carbon dioxide going up and up and up.
So when you say measured from Mauna Loa, I just want to make sure that everyone, no one has to feel as though they're supposed to know something that they don't.
You're right. Absolutely.
So yeah. What does it mean? What do you mean by the record? How do you measure it? What's Mauna Loa?
Okay, fair enough. Excellent. So there's something called the Keeling curve, which climate scientists know a lot about, and I don't know enough of the details. I don't want to speak to any huge details on it, but essentially there's been an ongoing experiment measuring how much carbon dioxide is in the Earth's atmosphere, and it's done lots of different places, but the origin of it was an atmospheric observatory in Hawaii on Mauna Loa. And there is seasonal change in carbon dioxide. It goes up and it goes down depending on how active the plants are in the area. But ultimately, it's been going up and up and up. It's sort of, it's a wiggle that gets higher and higher and higher. And when you compare that record sort of from the modern era to the carbon dioxide that's trapped in bubbles and ice, it's much higher than it used to be. And it's going up really, really rapidly. And it's changing much more rapidly than it has any time in the last few tens of thousands of years. So it's really, really quite dramatic. So I think I was going to go back to the arguing.
Go ahead.
Yeah, I mean, I think scientists like to argue about details, but they don't like to argue about things that are so obvious that they all totally agree on it. If anyone really, and there have been some disagreements there are a huge number of small disagreements, but the increase of CO2 in the atmosphere and how fast it's been going up and how unprecedented that is in any of the last recent time period in the Earth is not something that anybody argues about, because it's obvious to everyone who looks at the data, who knows how to look at the data.
And that's helpful. So how do they make that connection between the carbon dioxide going up in the atmosphere and the Industrial Revolution. So we know that they're correlated. In other words, a lot of people know, you've explained, I've read that the more fossil fuel that has burned, also the more carbon that's in the atmosphere. But how do we know that's not just a correlation? How do we know that's the cause?
Well, I think, in a sense, if you can just measure it coming out of the tailpipe. It's actually just the simple chemistry of how we get energy from carbon. All of these fossil fuels have carbon in them. If you heat them up and expose them to oxygen, they burn and you get heat energy out of it. And you can use that to warm your home. You can use that to run your car. We do it all the time. And the stuff that comes out of the tailpipe of your car is full of carbon dioxide. So, you measure that just as a pollutant. So in the same way that, literally it's kind of like where there's smoke, there's fire. Well, where there's carbon dioxide, there's fire too. That's how fires work.
So we can more or less know how much of this stuff we've burned, and it matches what we're measuring in the atmosphere.
That's right. And then sort of thinking about sort of trying to understand, one of the things that can be so tricky is if we do have such a thing as natural climate change that is not being caused by people, and we're worried that we're causing climate change, it seems at first like it's a tricky problem. How do you separate those two things? And the answer is really sort of in building models. So a lot of what climate scientists do is they build models, computer models. They've gotten incredibly more sophisticated in the last few years. And these are the differences in these models are the sorts of things that scientists argue about. And people make their careers over, well, my model's better than your model. And they're sort of kind of fighting that out in some way. But ultimately, they all show, in the big picture, they all show the same thing. And that is that when we look at the temperature of our planet, and when we look at the amount of carbon dioxide in the atmosphere of our planet, the only way we can explain it is by human beings burning fossil fuels. It wouldn't be doing, the warmer summers, the overall increases you said of about 1.1 degrees C, which is a little bit more than 2 degrees Fahrenheit. No one has come up with a way to explain those changes that does not involve humans burning fossil fuels.
And if I understand it right, people who make their careers in science live for figuring that sort of thing out, right? So if someone was going to come up with an alternative explanation, it would be one of these people who has dedicated their life to the search for that. Aha, I'm gonna be the one who figures that out, right?
Yeah, I think so. I mean, I spend a lot of time trying to teach science to, I love to talk about science. I love to teach science. And one of the things that I love about it is that people, and children in particular, are really natural scientists. I think we need to do a much better job teaching science particularly in our high schools. There's some wonderful science teachers out there, but we have a way of turning people off to science by making it seem like, oh, this is not something that belongs to everybody. It gets complicated and technical and jargony. I think it's important to realize that scientists are people too, and that they have, we're motivated like other people are, right? Like, I want a good job. I want to get paid well for my job. I want to be able to take care of my kids. I want to be able to do all that stuff. I feel really lucky that I get to, as a job, that I get to teach science and do science. But the way I would improve my career as a scientist would be to make exciting new discoveries, right? That's what I do. Most of the time they're really small, but maybe you want to try to find a big one. And one of the best ways to make discoveries is to look at what other people do and try to find where they did it wrong. Not because you want to be mean to them, but because, first of all, that's how science improves, by checking on each other. And second of all, I can make a name for myself. I'm the guy who disproved so-and-so. That's great for my reputation in science, that maybe I get a job offer somewhere, right? I mean, that this is, the motivations on the day-to-day life are not, it's not like scientists are like, living, I don't know, in a temple somewhere with their head in the thought chamber, just trying to, in the pure pursuit of truth. I mean, I like to think that I care about truth and I want to understand things, but also, we have these motivations. But all of that to say, if there were a problem with this thinking, there are a lot of scientists who are strongly motivated to find that problem.
How unusual is it to have this much consensus on a scientific fact?
It's kind of funny. In a way, it's actually not unusual at all, because there are some facts that are just that work, that explain things so well. And sometimes those are facts that are contentious for people outside of science. I would say that evolution is the sort of thing that is not at all contentious in science, because it explains things. It explains long-term things, but it also explains how, how some medicine, how some bacteria are resistant to antibiotics. That's explained through evolution. We're living through this, long, frustrating COVID times, and these new variants are a form of evolution. So I'm not a biologist, so I should steer away from that. But ultimately, things like evolution, things like gravity, it doesn't make a lot of sense to pick fights over those things, because there's no evidence that that's not how things work. It's kind of like, you might have an argument over what to have for dinner, but everybody can get along with the fact that we want to eat dinner at some point. So you choose your battles, and ultimately there really isn't any argument about it, because
the evidence is
everything so well. It's so clear. Yeah.
So one thing so I studied science as an undergraduate, and so but probably not everyone did. Certainly not everyone did. To come to conclusions, science uses data, and science tries to see if what they think is true predicts the next thing. So they test their hypotheses by saying, if this is true, then if I do this, that will happen. And if that turns out to be right, they say, yay, I can ask the next question. If it turns out to be wrong, I need to do something else. They learn, right? Science is learning.
Absolutely. And personally, I think that's why it's so much fun to do, because I get to keep learning, right? I'm not always right. In fact, I'm wrong a lot of the time, because I'm a human being. So I come up with an idea and I try to see if it's right. And if it's right, I think that's great. And I try to convince other people that I'm right. And if it's wrong, well, then I try something new. I think for a lot of scientists, it's a satisfying way to operate, because it's less about the show. It's not about it's about making an argument based in fact. And I think people who enjoy science find that pretty satisfying.
And so the scientific consensus is a result of the fact that the data is so strong and the hypotheses are so good at describing what's going on and predicting what's going on, that there's really not that much point to arguing about the big picture, even though there's some things around the margins of exactly how high the water is going to go, exactly how fast the temperature is going to rise, that sort of thing.
Yeah, exactly. I mean, really, sorry, there's noise out of my window, excuse me. But, really big claims require a huge amount of evidence, right? And you could become, you can make a career by making a really, really huge discovery, but you have to have a huge amount of evidence to back that up. If you were to somehow discover that all of these models were wrong in some fundamental way, that would be huge news, and that would make a career and a Nobel Prize. There's incentive to try to disprove really big claims like how fast the climate is changing because of what we're doing, but no one has found any evidence that has led them down that path. And so scientists move on to other things that feel like they're not wasting their time. and working on problems that need a solution, not problems that already have a solution.
So once there is enough evidence, the arguments die down, the likelihood that something radical is going to come up goes to almost to zero, but never totally to zero, because scientists don't like to say never. So scientists don't like to speak in absolutes, because that's not science then, right?
Well, you have to be open, right? You want to be open to being dissuaded. So I think it's the sort of thing where, sometimes I tell people like, well, what do I know for 100%? Well, I know for 100% how I feel about my children, right? I know for 100% what I believe, to be right. And sometimes I don't, but sometimes I really do. But in terms of science, every measurement you make has got a little bit of error on it. Every choice that you make could be a right one or could be a wrong one. And it's very difficult to live with uncertainty. I think, it's complicated. But it's something that you have to do as a scientist, because, someone is going to prove you
what
wrong.
A scientist would consider uncertainty, it means there is a chance in a billion that this might happen. But for those of us who live in sort of the everyday world of, I am 100% certain that, as you say, gravity will still work an hour from now. I am 100% certain that the Earth will keep rotating and the sun will rise tomorrow. Most scientists won't say 100%.
Yeah. It was interesting. You made me uncomfortable saying 100%, because I think in a way, one of the things about a lot of scientists is because we try to be so skeptical of our own work and of the work of our colleagues. As soon as somebody says 100%, well, then I figure they're lying to me, because nothing is ever 100%, except for how I feel about my babies, right? So
they'll be teenagers.
They are teenagers, actually, yeah.
Oh,
and they're frustrating too. Sometimes I have mixed feelings about them, but deep down inside, I know just how I feel about them. But yeah, I think it is that, and I think that's one of the problems with the communications. You're like, well, why won't he say 100%? Well, it's because I won't say 100% about just about anything, because I could be wrong. I have to be ready about being wrong about things. If I were a betting person, boy, oh boy, would I bet on, on gravity existing tomorrow. I feel the same way about gravity existing tomorrow as I do about the fact that human beings are causing the climate to change. I think
that is absolutely, and most scientists, there's actually this great, I'm not sure if you've seen this study that actually surveyed every paper in the last 20 years that talked about climate change, and then talked to their authors, surveyed their authors to see, and the first version of that study said 97% of scientists feel exactly as you do. And the second one said 99%, but one of my scientific advisors takes issue with the 99%, so he wants me to say 97.
Right.
So, but that's a lot of consensus.
And that's such a classic scientist thing to do, right? I mean, the different, right? If I get a 97 on a math test or a 99 on a math test, I'm feeling great about both of them, because those are like super high A's. Who cares about the difference between 97 and 99? A scientist does. That's because, but the answer is still the same. Yeah, we're doing it. Everybody knows we're doing it. And it is, and I think it becomes frustrating for people who know the science to sort of feel like they have to relitigate this over and over again, right? I know the sky is blue. I know gravity will be around tomorrow. And I know that human beings are causing climate change. And everybody else who listens to it does too.
And that was kind of why I loved your lecture so much. And it was because when the students asked you these questions, you were thrilled that they had asked. You were happy to answer that as clearly and as patiently as you could, because you wanted them to learn.
Right.
And that's super helpful, because it's hard to follow the science, especially when there are some people out there saying, oh, it's not true. I want to talk about one more thing before we finish up, which is that in a certain way, the fact that humans are causing climate change is a good thing, because it also means that we could not cause climate change, right?
Right. Yes. I think that would be swell. I think we should do that. And I think, and I think that it is one of these things, right? We spend so much time. I mean, this is kind of going to uncertainty, right? We spend so much time kind of pretending that we live in a black and white world. And I think a lot of times the media and politicians are very successful by presenting things as if it's one or the other. When anyone who spent any time dealing with a complicated problem realizes that it's complicated, that it's shades of gray. So I think so too with climate change, we have some folks who are like, yeah, I don't buy it. And then that can be frustrating because you could say, well, what don't you buy? And on the other hand, we've got people who buy it and are devastated by it because it feels like, it's the end, we're doomed, right? And I think that, in trying to convince people who don't agree with climate change, there are these doom and gloom scenarios. I was talking about this terrible mass extinction, and I think we really are in a crisis moment. But just because we're in a crisis moment doesn't mean that we can't make good choices, doesn't mean that we can't change the direction that we're going. And more importantly, it means that we need to. It doesn't mean that everything is going to be perfect, right? I mean, we have, there's been record high temperatures recently in India, shockingly high temperatures. And when things get really, really hot, people die, particularly old people. And this is sad, and it's tragic, and it's awful, and it's worth fighting against. I don't like the idea of elderly people dying of heat exhaustion. And this is happening more and more, and it will continue to happen more and more because of what has happened.
That more people died in heat waves than fires.
I mean, it's possible. I don't know that, but it's entirely possible.
Try to look that up and share it with share the link to some of that data when we put this out there.
So bad things are happening. Bad things have already happened, and bad things will continue to happen. But that doesn't mean that it's all over. It just means that the sooner we start making better choices, the fewer of these things that will happen in the future.
So in terms of the choices that we need to make, there are a lot of different choices. We can choose to drive or take a train if we live in an urban area. We can choose to have an electric car, put solar panels if we're wealthy enough to make those choices. What are some of the other choices we need to make? And I also want to come to the fact that we're talking about systemic problems. We need systemic solutions, and that means we kind of all got to get coordinated around this.
Yeah, absolutely. I mean, I think that this is the kind of a problem, right? This is a kind of a problem like COVID has been, but even more, where we just want to throw everything at it that we can to fix it. And if that can mean personal choices, but it's got to be more than that, because there are so many sources of carbon dioxide in the atmosphere, and that they're caused by things that we don't even think about. It's not just when you get in the car and turn on the key, and are you driving a hybrid or an electric car or a great big truck. It's also the concrete that was poured to make your home, and the concrete that's being poured to make homes that are being constructed today. That affects the atmosphere. So I think what we need to do is make big changes of what we do as a society, both the choices that we make, but also the regulations that we have. So I think the best thing that can be done is voting, and is working to convince legislatures, is working to be engaged, to set policy that will promote putting less carbon into the atmosphere.
So as individuals, we can make choices, but the biggest sources of carbon dioxide are not necessarily people, but the industries that supply people with energy. Right?
Exactly. Yeah. And it's the power plants. It's the transportation. It's the giant shipping systems.
So we want them to make different choices. So it's
Yeah.
not just about whether you have a hamburger or a Beyond Burger. It's really more about like, how do these what are the choices that these big companies are going to make?
Right.
And I think that's where voting has a really big power, right? Because we can't, it's not very easy for us to help companies make different choices, but government action can kind of do that.
Some really forward-thinking companies are already making these choices, and they're making these choices not just because they think it's the ethical and right thing to do. They think it's going to make them more money in the long term. You know, there's some of the big shipping companies are talking about looking at alternative fuels for their big ships. When you look at, you know, the parts of the government, you know, the Pentagon has big climate change plans. They're not arguing about the science of climate change. They're thinking about how that's going to affect their job as in terms of being the Pentagon and being in charge of defense. So groups are moving in that direction of their own accord, but also, I mean, that's what government is for. People deciding that this is the policy that they want, people recognizing that climate change is a problem, and sending the orders to their governments to make those changes.
One of the things that I've learned as I've been trying to learn more about climate science so that I hopefully can help other people understand it well, is that we actually have a lot of the answers at hand. Like the ability to take most of the carbon out of our electrical system. We have that if we want to have that. What is the difference between solving the whole problem and solving what we can? We have a question from the audience too. I'll give you that one too. How do scientists know how fast we need to change? How do scientists estimate how much time we have to turn the ship around, to stop putting carbon into the atmosphere and start taking it out?
Sure.
So we've heard 10 years. Where does that number come from?
Well, I think that that's a great question. And as soon as we ask anyone to make predictions for the future, uncertainty starts to change more, right? We've got the certainty, you know, there are little arguments about how fast it's gotten warm so far, but when you start moving to the future, then you have a lot more uncertainty. What are the choices that we have made already? What are the choices that we're going to make? And how fast are they going to affect that? And I feel like that's where there's more uncertainty and more discussion. And also, you know, this is kind of like, it's like forecasting, right? There's the longer out in the future you forecast, the more uncertainty there is. And you know, when we look at the weather forecast on TV, we sort of know that in our hearts, like, oh, it's going to be sunny, you know, next weekend, but I'm going to wait till we get closer to see if it changes. You know, they don't actually show you the uncertainty, but everybody involved in the forecasting knows that there's uncertainty. So I want to say all of that sort of thing. So I also want to say that, you know, the phrase so what am I trying to say here? I'm just trying to think of the right thing. I don't think that there's a clear answer how fast we need to change, but I know that we need to change. We know that we need to change quickly. And part of that is because it's not an all or nothing question. It's not that everything will be totally, unlivable in the future. It's just, it's less livable now than it used to be, and it will continue to be less livable. So it's not one of these like, oh, okay, if we don't do exactly what we need to by 3 weeks from now, it's all over. It's just that the longer we delay, the worse off our children and our children's children will be. And so it's not about how. So the answer is change a lot and change it as quickly as we can.
And it's not going to get any easier to fix, right?
No, it's we're moving in the wrong direction. So it's kind of like if you're driving off the road, why do we ask the question, okay, well, how much further off of the road do I drive before I steer back on, before I'm going to flip the car? You know, it's better to just say like, well, you know, you're moving off the road. Let's steer back on the road. Let's not try to see how much we're going to push it in order to flip the car. At least that's the way I think about it.
Yeah, no, I think that's a great analogy. We have another question, which may be a little outside your area of expertise, but I have a feeling that you can do this.
I got opinions.
I've read books. We've been eating meat for millennia. Is the issue with eating meat or how we produce meat?
Oh, I mean, I think the answer is yes, across the board with all of that. When you just want to think about I think it is, we've been eating meat for millennia, human beings, you know, I have pointy canine teeth, right? I mean, that's I evolved that for a reason. Now, but we also, you know, our behaviors that we have right now are not fully dictated by the things we've been doing for millennia in our evolution. We can make choices. So from a standpoint of the carbon effect, we released eating meat and eating certain kinds of meat, red meat in particular, particularly the way we do it puts more carbon into the atmosphere. But I guess I also think, you know, there isn't going to be one silver bullet. There isn't one solution to climate change, and there isn't one culprit to climate change. I think it's about sort of changing behaviors and also changing policies. So, you know, eating meat all the time is not good for you, right? We may have evolved to eat meat and eat for millennia, but it's not the healthiest way to live, and it's also not the most carbon neutral way to live. So reducing red meat consumption and changing the way we farm our meat are both ways to reduce climate problems, but they're not necessarily in and of themselves going to solve all of the problem, and they're not in and of themselves responsible for all of the problems. So there's no like,
yeah, what I've heard, and you know, in my inexpert attempt to become at least passably conversant in this stuff, the sort of shorthand I've seen is that a third of our carbon problem is coming from our electrical grid. A third of our problem is coming from transportation. Or am I doing, you know, one chunk is the electrical grid, one chunk is transportation, one chunk is manufacturing, and the last chunk is agriculture. And decarbonizing the electrical grid, we have what we need. Decarbonizing transportation, we can get there from here. Decarbonizing manufacturing, a little harder. Decarbonizing agriculture, there's some pretty good stuff on the horizon. Like this stuff isn't about hoping for a miracle or hoping that everyone's going to suddenly be vegan, right? That's not what the solution depends on, but more of a coordinated effort toward getting those things down, right?
Yeah, I think so. Like, you know, a little bit from everything will help. So, you know, this is just a personal choice, but I just think to myself, like, yeah, okay, I like a burger. But if I had a burger every day, I would be a less healthy me, and I would be making more, you know, that would have a stronger carbon impact. So I tend to think like, you know, sometimes I should go for the salad for lunch. And there's more than one reason that I should go for the salad at lunch. But I also shouldn't be consumed in guilt that I had a burger that one time. On the other hand, all of this is just part of the story, and I should really be worrying about where I get my electricity from, and particularly what kind of a policy we should set at the governmental level for how electricity is allowed to be generated, because that's a bigger impact but everything helps. So, there's lots of reasons to eat less meat, but it's not going to solve the solution, solve the problem all by itself.
So we understand the history. Thank you for that. And we understand how we understand the history. We understand what's happening now. We understand, and this is something that I really didn't understand a few months ago that I'm starting to really understand now, that solutions are at hand. This is not a doomsday scenario. It's just a wake up and smell the coffee scenario. And, it's coordinated deciding to do something about it. That is where we're at. We've gone pretty long, and I just really appreciate you spending the time, but also how much you want to teach and how you're helping us to sort of not just say, this is the fact, you agree with me because I'm right, because I'm the scientist, but help us understand how scientists think and why scientists think that this stuff is true. I think that's incredibly helpful and surprisingly rare.
That's a problem. I mean, it's a problem. We got to work on it.
Well, thank you for helping solve a little corner of that problem in this little corner of the world. I really have enjoyed talking to you and learning from you. And I hope to speak to you again more.
Yeah, absolutely. This has been a real pleasure. And thank you so much for the work that you do. It's really important. And I'm grateful to be a small part of it.
I get to learn every day too. That's the best part.
That's good. That's good stuff.
All right. Thank you, Zeb.
All right. Thanks. Bye-bye.
Bye-bye.